Good morning, everybody. Welcome to the P1 training session for Work Package number 3. There will be 2 sessions of Work Package number 3. The first session is today, and the following session will be on Wednesday next week. Okay, and this is the agenda for this session. First, we will have a first block consisting on these 3 points: workflow overview, system component specification, and requirements formalization. After this block, we will have a set of questions, or maybe in between, when we change the presenter, you can ask some questions too. Then we'll move to another block, which is requirements validation by UC3 and TRC, with questions also included here. And the final one is the functional refinement slot, consisting on 3 blocks again, and at the end of it, a set of questions. Okay, please take notes of your questions to ask it at the end of each speaker or in the question section. Okay, so I switch the presenting rights to Stefano Tonetta by FPK, and then we can start.
Thank you, Luis. So I will start this training session with an overview of the methodological workflow that we are following with the WP3 techniques, which is focused on architecture-driven assurance. So first of all, let me clarify what we mean for architecture-driven assurance. So we have this concept at 2 levels, both a technical and a process level. At technical level, the idea is to exploit the architecture to perform early verification, validation, and analysis on the model that we are doing in order to build a correct and dependable system. In particular, we support the decomposition of requirements along the system architecture, ensuring a correct refinement with the contract-based techniques. We have other techniques in order to ensure the quality of requirements that range from formal or semi-formal specification analysis based on the textual version of the specification or the semantic, the formal specification of the requirements. And we have also the possibility to derive safety analysis from the architecture, injecting faults in the models and applying different techniques, mainly based on monitoring on simulated traces or the generation of minimal cut sets. So all these techniques provide different artifacts that can be used as evidence for the safety case from both the modeling and the analysis point of view. So we provide techniques to generate this evidence and also to generate documentation argument fragments that can be used to build a complete safety case. So the idea is to reflect the architectural choices and the analysis results that we produce during development of the system in the safety case. So the idea is to move from a safety case that is based on the process of the system and the validation done after the development to a process in which we enrich the assurance with all the artifacts that are built during the development, and in particular the analysis results that are generated in the early verification validation of these models. In WP3 of the AMASS project, we developed different techniques, and they are provided by different partners, so there are heterogeneous techniques that the idea is to apply them to the same model. So we will see that there is also ongoing integration of further techniques, but the idea is to apply these techniques to the same chess model and to collect different analysis techniques integrated in the same tool. Of course, there is still ongoing work. We don't have yet a single model example, but we have an uniform workflow that is detailed in also the methodological guide documented in the deliverable 3.7. So the idea of the workflow is to have a standard sequence of phases that go from the system design to the safety analysis to the safety validation and safety case. And apart from safety validation, each of these phases is supported with different techniques. In particular, today we will see part of the techniques that support of the system design, in particular the system definition, the formalization of requirements, early validation techniques for requirements, functional refinement, and then we can also specify behavior and extend the behavior with faulty specification. We have techniques for early verification of this functional view of the components, and from this system design we can derive also safety analysis as anticipated based on fault injection and different techniques for faulty generations. In the safety case, we generate evidence. We can link the architectural models to the assurance. We can generate reports on the analysis performed, and we can also generate fragments, argument fragments that can be used to build a complete safety case. So I now give the presenter role to Stefano Puri, who will start the details on the system design.
Yes, so thank you, Stefano. So I'm going to share my screen. Okay, sorry, just I'm not able to switch to the presenter. Can you see the slide in presenter mode or? Hello?
We can see only the PowerPoint. The presenting mode is not working. It's not
also,
working.
it does not work also for me. I don't know why.
But you can keep doing in the edition mode. No, it's not a problem.
Okay, sorry for this. So I'm going to introduce you a support that we have in AMASS, in particular in our tool environment regarding system component specification. So basically the tool that can be used for system component specification that has been adopted in AMASS and in the OpenCert environment is the chess. So briefly, let me just recall what chess is. So chess is first of all is a model-driven methodology for design, analysis, implementation of critical systems. So it is so first of all, it's a methodology which comes with the dedicated modeling languages, which is based upon the OMG modeling languages. So basically, UML, SysML, and Marte. So the chess modeling language is defines so a profile for these standard languages by tailoring the possible set of constructs that you can use, and by extending some base construct which come with these standard languages. Basically, what the modeling language provides. So the modeling language provides modeling support for the dedicated chess component model, which is more relevant to the software design. Also, the language provides some extension related for the modeling of the safety behavior and the contract-based approach. In particular, these two areas, so the safety behavior and the contract-based approach, is of particular interest in OpenCert. So during this session, I will talk about the contract-based support, and then in the different session that we will have, we will introduce you how it's possible to use also the safety behavior support. So chess is a methodology and the language, and it has a dedicated toolset, which is based in Papyrus. So basically, Papyrus is the tool which is available in Eclipse about the modeling, which support the modeling of UML and derived languages. And in chess, we have extended the Papyrus in order to offer an extended environment for the modeling of contract, and also to allow different kind of analysis starting from the provided models. And we have also support for coordination, but okay, for the moment, for what regard the features that are relevant for OpenCert, we will focus upon contract modeling here. And in this section, then we will check about the support for analysis in a different section that we will provide soon. So chess is available as PolarSys project. So just a few information about Papyrus, which I recall here is the tools which has been used for chess in order to implement the chess extension. So Papyrus, as already said, is an Eclipse tool for UML, SysML modeling. It has a very good support for implementation on domain-specific languages, which is basically can be implemented as profiles of the standard OMG languages. It has provides a very good customizable environment. So I will show you later what we have done regarding the chess, the customization. And I think it is a lot of information can be you can find some very useful user guide about Papyrus with can be useful also while working with chess. So I recommend you to also, if you are interested, and you don't already know Papyrus, so you can take a look at the user guide that you can find on the wiki of the Eclipse. So let's start about to see how we can perform the system component specification. So the first step is to create a chess project through the dedicated wizard. So here I can switch to the chess environment, which is embedded, which is also comes with the OpenCert bundle. So here I'm using the P1 OpenCert bundle. So here I can, from the Project Explorer area, I can select a new project, and here select the chess project. I will show a few examples about the modeling of a wheel breaking system. So wheel breaking system is a quite famous system that is also addressing several papers, and so basically address the modeling of a system which has to control and activate the braking on a wheel according to some signals that arrive from the pedals. Basically, here you can see that the project has been created. So here we have you can see the main areas of the chess editor and the Papyrus, so the Papyrus 1. So in particular, here we have the model explorer, where we can see the model in a 3 view, I would say. And here we have in the center we have the area for the diagrams. And as you can see, is here the chess automatically is created according to a predefined structure, according to, in particular, according to predefined views that comes with the chess methodology. So we have the views are presented here as dedicated packages. So we have in particular the requirement view, where requirements can be modeled, the system view, where we can model the system specification, the component and view is more related to the software part, so the modeling of the software architecture, and the deployment related to the hardware that on which the software is deployed, and so it runs. Then we have a view regarding to the analysis part, so where you can provide information in order to run particular the analysis that are available that can be invoked through chess. And then we have another view more related to the software implementation part. So for this session, I will focus mainly on the requirement and the system view. And so I will consider on these two views. So let's start with the to see how we can design our system components, so the specification. So I will show you. I'm going to show you how it is possible to define requirements. During this session, I will focus just on the basic support that you can have by using basically the Chess and Papyrus tool, but I would say that what you can the support that you can have by using the plain SysML language. If you are interested, in Papyrus comes with the advanced support for managing requirements, like for instance the possibility to import it from different sources, external sources. That can be an Excel file or something more advanced like set of requirements expressed through the requi-if, which is a standard interchange format for requirement specification. So if you are interested in this extended feature, you can have some documentation here. Then I will show you how it is possible to define the architecture, so the definition of the blocks, in particular with the it can be possible to define its interfaces. And also I introduce the diagram can be used to specify the internals of the blocks. So additional information about how the blocks is modeled. So let me just switch to the chess. So I can starting to provide some requirements here. So I have to create a requirement diagram. I have to go to in the requirement. I have to select the requirement view, right click, and select here new diagram and SysML requirement diagram. Okay, here I have the palette, which allows me to create all the information that can be related to the requirement design, I would say, requirement, so specification. Basically, this is a plain SysML support. So let me just add a requirement here about our well-breaking system example. So here, let me just take a break. Let me just provide some an example of requirement about some constraint about the delay that can be should put between the command that can be provided to the system, for instance, through a pedal, physical pedal, and the command that the system has to provide to the actual brake to brake the wheel. And here are you in the SysML tab, you can provide the text for the command. For instance, the delay. Okay, between a break and its execution, for instance, shall not exceed, for instance, 10 milliseconds. Okay, this is could be a requirement for our system that I have expressed here in a natural language. Now let's move to the system architecture and see how I can model a component which can further can be designed to satisfy this requirement. So in order to model the system component, I go here in the system view, I right click, new diagram, and in this case I select the block definition diagram. Okay, let me just change the name of the diagram. System. Okay, here you can see that I have the diagrams come with the palette which is specialized by chess. So here you find the entities that are allowed by the chess profile. So in particular, I can create my root of the system that it is identified by the keyword system here. So this represent my wheel braking system. Okay, I can start to detail the interface of this system by providing the ports that are interaction points between the system in this case and the environment. So I can create flow ports directly here in the block definition diagram. For instance, I can create, as I will say, I can assume that I have some signal input through a physical pedal. So this represents the input that come from from a physical pedal, and I can provide also the type for the port. And here, so I have to switch to the UML tab. So here you can find a lot of information. In particular, what we need is to provide a type for the port. I can use some predefined primitive type here. For instance, let me just use the Boolean in this case. I can also, in case, create additional data types by using this construct here. So if you need some further data type, you can create it. Let me just use this basic one. Okay, we can assume that we have this information has been made redundant in some way. So I can model the fact that I have two signals from two pedal poles, so the information has been made redundant. In order to, I can also use some copy and paste facility. So here I can copy the port and paste it here. So this is just so I can, this way I can just change the name, and the copy and paste facility allows me to derive all the information that I have is also copied from the original entity. So the type, for instance, here is already available. I can make it appear here this way by drag and drop. Okay. So this, I think, that it's all for what regards the input port. For in order to model the actuator part of the system, so I can create first of all, I have to change the direction. As you can see here, I have predefined. By default, the system provides me in out direction. In this case, I say that these signals are in input. Okay, so I can change the direction here. Then I want to create a port for the actuation. So I can create a new port here. Let me just call it command. And this is, let's say, is an out port. And for the type, let me just continue using the Boolean type. Okay. So in this way, I can formalize the interface of my system, in particular how the information that can flow in and out from my system. Okay, I can start to introduce another way to represent the ports in here. So, and in particular by using the internal block diagram that I will also use later during the refinement step. In this way, I can select. I have to select the entity that I want to for which I want to show the ports. I have to select a new diagram and then internal block diagram. Let me just rename this. Okay. Okay. So here you can see the internal block diagram of my system. I can create also a port here, also with the already predefined direction. So this is another way to do it. If I have already ports defined for the block here, I can make it show by pressing F4 on the keyboard, and here you can find this window through which I can select what the entities that I want to make it appear on the diagram. So in this case, you can see that the ports that I defined before are represented here. Okay, I think this is all for what regard the system component specification. I can move to forward with the presentation. Which is about the requirement formalization. So the next step in our design is to provide a formalization of the requirements that have to be fulfilled by our system component. So by doing so, our approach is to provide a contract-based approach, where contracts are basically built upon the concept of formal properties. So here I will talk about formal properties, and then later we will see how contracts can be specified. So what is a formal properties? Formal properties in chess is a special kind of constraints of UML, through which it's possible to use dedicated languages, constrained languages, to provide a formal specification of a given requirement. Later, when we have a proper set of formal properties, you can basically collect this formal property into and build the contract. So I'm going to show a demo about how it is possible to create formal properties for a block, and using some advanced tool facility in order to provide the specification of the formal property, and then how it is possible to link the formal property to the requirement that is formalized by the formal property itself. So let me switch to my model. So what I want to do here is to provide a formal property for the whole breaking system block, which formalize the requirement I have put here about the break delay. So in order to provide the formal property, here you can see that we have a special set of constructs related to the contract design. So here you can find the formal property. You click the formal property and you create it. And you create it in the constraint compartment of the system component. Then you can switch to and you can select the formal property just created. And in the properties view, you can see that the property editor appears. You can click it. And then here you can find a specialized editor for LTL language. So here the support is related to LTL languages. They can be used to formalize the requirement. And also, so here you have an area which also implements a content assist editor that help you to define the expression, the LTL expression for the formal property. So in this case, for instance, I have to create the formalization. So I have to press Control plus space, and the tools, the content assist provides me the list of keywords allowed by the LTL language. In this case, we are focusing on the OCRA syntax of the OCRA, the LTL language. Here you can see some keywords defined by the language, and also you can find some property that you can use in the expression. So this ports you have defined for the port. So your formal expression can elaborate about the properties of the behavior that is expected to be implemented, or is expected that we will that is expected to be implemented by the system, or some behavior that you expect by the environment where the system will be placed, will run. So I can start to write something like this. So for instance, so the constraint is about some timing property about the reaction of the signal in input and the actuator, the signal that has to be put in output for actuation. So I can say something like always. Let's say change. Here I use the pedal post 1 port. Let me just first wrote the. Or you can see how the keywords are recognized by the editor, and they are properly highlighted. So I was just saying that by change, if something change in input, pedal post 1, pedal post 2, I have put some constraint on the time that the command has to be provided. So time until change, and so here the break line, the command, the break line. Here it has to be okay, minor. Minor or equal to 10. Okay, so in this case I formalize my requirements that says that okay, the actuation has to be performed in 10 milliseconds according to the command coming from the environment about the braking. Okay, if I here I put something that is not recognized as in this case as a property of the block, the editor shows you an error here, but also here attached to the formal property. Then this way I can formalize the requirement. What we have to do now is to associate the model the fact that this formal property satisfies a particular formalizes the particular requirement. So here I have to select the formal property and go to the profile tab here. Here you can see this that the formal property comes with two predefined attribute, so in particular the formalized requirement 1. Here I can select this add element and then select the requirement that is formalized by this formal property. In this case I have just the break delay requirement. So this is the step that has to be done in order to provide information about the requirement that is formalized. Okay, I think I have covered all the steps for this part, so I would move now the presentation to Alberto for the next part. Can you do it, Luis? Can you?
Yes, yes, of course, I will
Okay.
do it.
Okay, thank you.
Okay, Alberto.
Can you see my screen?
Yes, yes.
Okay, so in this section, I'm going to talk about how to define contracts in the context of system design. So first of all, let's see what is a contract. So a contract basically wants to describe the expected behavior of one component, and it's composed by two formal properties. So we have an assumption that basically wants to describe the expected behavior of the environment, and another property that is the guarantee that basically describes what the component, what is the expected behavior of the component, assuming that the assumption property holds. So this is the basically the concept of contract. Okay. So now I'm going to show you how to create and edit a contract in Chess. So let's continue with the example of the wheel braking system. So here we have one block, one component that is the system, with the two formal properties. One describes the expected behavior of the environment, that is the WBS assumption, and the other is the wants to describe the expected behavior of the component. So in order to formalize this concept of assumption and guarantee, we need to create a contract associated to the system component in this case. So let's select the component, and here in the properties tab and the properties view, click on contract editor, and from this editor it's possible first of all to create a contract. So in this area we edit the contract name. Here there is a pop-up that asks if I want to create a new contract or instantiate an existing one. We want to create a new contract with no formal properties associated. So here, as you can see in the Model Explorer, we have a new contract that is created. Now, in the contract editor, we select the contract that we have already created, and here, as you can see, there are two textual area, one related to the assumption and the other related to the guarantee. And in this case, we don't want to create new properties, but we want to link the properties that we have previously created, one as assumption and the other as guarantee. So we click in this button here, and here we select which is the formal property that acts as the assumption. And we do the same for the guarantee. Okay, so as you can see here, we have the expression that is exactly the expression of the formal property, that in this case is the WBS assumption. And here we can edit the properties. So here, for example, if we change using the contract editor, if we change the body, let's say, of the properties, if you select in the Model Explorer the formal properties, as you can see, it's the body of the property is synchronized, so you can edit directly the formal properties in the contract editor. Okay, so here I show you how to create a contract starting from the formal properties, but it's also possible to create a contract from scratch and then create the assumption and the guarantee. So, for example, if you want to create a new contract, we select the component, we select the contract editor here, and we create a new contract. Again, we want to create a new contract with no formal properties. So here, as you can see in the contract list, there are two contracts, the one that I created before and the new contract. This second contract doesn't have formal properties associated to it, so I can click this button to create a new formal property that by default is true. So in the Model Explorer you can see a new formal properties that is automatically created. And we can do the same with the guarantees. So we can select this button, or we can start just editing in the textual area, and automatically a new formal property is created and is associated to the contract. So basically, this is the main workflow to create a contract and to edit a contract in the context of the system design. Okay, so if you have a question about this section, about the requirement formalization, you can ask me. Otherwise, I can pass the role to the next speaker that will talk about the requirement yearly validation.
Do you have questions, either for Alberto or Stefano, or the other Stefano?
I would like to ask about the navigation from the formal property to the natural language description of the requirement, if it is possible to automatically go there, or how is it done in the easiest way to go quickly from the formal requirement to the natural language description.
Who can answer this?
Yeah, I can. Yes, currently, so as I have shown you from a formal property, you have the possibility to link the requirement which is formalized. So we don't have any some kind of way to, for instance, show the attach it to the formal property the requirement which is formalized. In particular, its definition in natural language. So currently, the only possibility is to just to check the requirement which is formalized and then select the requirement in the model. So it's not there is no there's no other way for the moment to move from the to see the requirement textual in natural language which is attached to the formal expression.
Okay. Another question. In the property editor, I saw during the auto completion some words like der or fall. Where do these words come from?
Yes, this word comes from the definition of the Okra language. So, so the modelers, which the architect, which is going to perform this step, so the formalization of the requirement in this case has to be aware of the language that is it proposed here. So it has to be a knowledge about it, how it is defined and the construct and the semantics that it is associated to the language.
Okay. So this grammar of this formalization language is available somewhere, I expect.
Yes, it is available. So it's available on the internet. Yes, right. So Stefano, so it is the user guide, the user manual of the Okra languages is publicly available.
Okay.
And yes, we can provide its link.
Do you have more questions? No? Okay. Then the next one is Stefano. The last part of the session is functional refinement. Okay? So Stefano Puri, I transferred you the presenting rights.
Okay, thank you. Thank you, Luis. Okay. Can you see my screen?
Yes, perfect.
Okay, thank you. So let me continue this session by talking about how functional refinement can be performed within the chess tool. So here I going on with the system component specification demo that I have been introduced before. So in this part, so the goal is to model the composition of the system. So this is something that, related to what Luis already introduced when talking about the product breakdown structure. So here the goal is to address the modeling and the implementation of the system by considering that the system is composed by the sum of more elementary parts. So the goal is to address, to manage the complexity of the system under modeling. And so I'm going to provide you a demo about how this decomposition can be modeled in the Papyrus and Chess. And so by using what SysML proposes, and in particular by using the block definition internal block diagrams. And then I will also relate this decomposition of the architectural part to the contract specification of the different elements of in the different that have been defined at the different levels of the hierarchy. So let me switch to the tool. Okay, so here I continue with the model example I've started before. So this is my wheel breaking component represented the wheel breaking system with its input-output port and from a property. I have also here completed according to what has been presented by Alberto. So I have created a contract here for that basically aggregates the two formal property, one represented as the guarantee that I've shown before, and I've also here created a formal property about a possible assumption that we can put on the input port. So here we can formalize how we expect the environment and should behavior in order to properly be sure that our component can guarantee what we have written in the other formal property. So the goal here is once we have defined the interfaces of the component, and when we have defined the contracts for it, we can start by we can go on with the decomposition, so by modeling how, as I was saying, how the system is actually composed by more elementary parts. So in this case, we can imagine that the wheel breaking system basically is composed by at least two more elementary block or subsystem in this case. One could be a braking system control unit, so that I call it BSCU. So this is will be the control unit that will take in input the command from the environment regarding input and post, and perform some control algorithm to send out the actuation, the command for the actuation. And we can think that the actuation will be performed by either some a kind of hydraulic subsystem. So here, let me just create a new block. Sorry, I've used the system. I've created the system block, not just the block, but here I would avoid to use the system notion here. So I can take this opportunity to show how it's possible to remove this tag here. So we see if we don't want to. So we have to go to the profile. Okay, so no, it's not allowed. So let me just check select the block, not the system block, and so this is the other kind of block that we need to build our top level system. And here I have to perform what I did for the WBS block. So here again I have to first of all define the interfaces for these other blocks, and so given that these are okay, I have created this block from scratch, so they are empty, but here I could reuse some existing blocks, maybe define it in some model libraries that I have. So here I could realize the system decomposition. I could model the system decomposition by using not only top-down the modeling approach, so the top-down decomposition, but also I could realize the hierarchical structure by using a bottom-up composition approach. So I could take some existing block here and use this block as parts of a more complex block. And so the approach that we are proposing here, so the component-based approach plus the contract-based approach, and are especially useful for definition of modeling of components that can be designed independently and then can be put as part of more complex systems. So in this case, I can just as an example, I can think that these are new blocks that I have to model. So I can imagine that the control unit here will need the input from the environment. So we can imagine that it needs the input from the two pedal pods. So here I can again use the copy and paste feature. So I copy the ports that I've created for work breaking system, and I can paste here. Okay. So I can make the port appears. And then I can imagine that I would also have some out ports coming through the control unit. So basically here, let me just reuse this port that I've already provided. And the same for hydraulic. So the hydraulic subsystem, in my mind, will take the command from the control unit and will perform will properly drive the physical brake that will break the wheels. So this represents the physical part. So I can imagine that we will have an input port here for representing the command coming from the control unit. Let me just continue using my the Boolean as primitive type, but of course we can use data types that are maybe more close to the real case. So and I was saying also, yes, here I will need also an output port to model the actuation and the fact that yes, to model how the fact that the hydraulic will command the actual brake. So here, just for simplicity, let me just reuse the port that I have created before, so the output port. Okay, so when we have the proper defining the interfaces for these other blocks, okay, we can start formalizing the fact that my system is decomposed, is made by these other blocks. Here I can use the direct composition relationship in this way. Sorry. So from the part for the system that had to be decomposed to the more elementary parts. So in this case, I'm saying that I'm modeling the fact that my system is decomposed by this other system. Here I can just rename the name, this name associated to the composition relationship, and I'll show you how this name appears also later when we will talk about the internal block diagram. And okay, this is what we can model here in the block definition diagram. So I can represent the decomposition in this way. So I can in the model explorer, I can see that the tool automatically for the WBS system create two properties like this one, which are actually which describes actually the parts that have been created in the context of the WBS system. So these are actually describe the decomposition in the UML model. So these, so in the model explorer you can find the block created, which are being created independently from the WPS, and then here you can find how these blocks have been, I would say, instantiated and become parts of the WPS. So in order to better describe how these parts have been, so the roles of the how to better describe the roles of these parts in the context of the WBS, it is necessary to switch to the internal block diagram of the decomposed system. So I have already, if you can remember, I already created the internal block diagram where I just showed the ports for the blocks. Now I can details how the parts can play the roles here, and I can again by pressing F4 on the keyboard. Here in addition to the ports, I can decide to show the parts that I have already defined by using the composition relationship in the block definition diagram. So I select these two parts, And the tools represent the parts as in this way. So the parts have this notation. So they have the type, BSU in uppercase, and also the name. The name, if you can recall, is given by the name that has been also present here, associated to the composition relationship, and is also the name of the property that you can find here. So this is a different way to represent the same information about the property here, or by using this composition relationship here. And if you can remember, I have created ports for the internal blocks. So ports are attached to the block. Indeed, if you see in the Model Explorer, the control unit and has some ports that I have defined. Also, the hydraulic block has ports. So the ports are associated to the block, and each part that is typed by a given block inherits the ports that have been defined for the block itself. So what does it mean? So it means that in this case, this part, which you can think about it as an instance of a BSSU block, inherits the three ports that I have defined for BSSU. So here I can show the ports. I can simply drag the ports from the Model Explorer to the parts of the same type. So here I can representing the ports also. So the two ports for the pedal post, and the one from the command. Okay, let me just move the ports according to a more intuitive way to see input and output. Okay. Now I can I can model the delegation of ports, and so how the ports of the parent block is actually linked to the port of one of its parts. In this case, as we say, it's expected that the control unit actually takes the signals coming from the environment, and the signal is actually taken from the ports of the parent. So the idea is that all the information is flows through the ports of the parent and into the input port of the internal parts. The same for the output port. So I have said that the hydraulic has the role of applying physically for instance, the pressure on the brake. So it has an output port. So let me just show it here again. So this is the input port. So this is the one in output that I'm thinking that I think it will drive actuate the braking signal. And so I can also model the delegation between the output port. So in this case, the output port will be of the Wilbecker system will be just the output. I would say the signals coming through out of the output port of WBS will be actually the signal that's coming out from the hydraulic part. And then I can, once I have delegated all the ports for the top level system, I can connect in ports which are internals of the parts. So in this case, I can use internal block diagram to also to represent how the parts can be connected. So it is important that all the ports of the block that we are decomposing are delegated to internal parts, because we are here thinking about a hierarchical design where decomposed systems is decomposed block actually provides behavior through its parts. So a block which is decomposed as not behaviors from itself, but provides the behavior that is implemented, is actually implemented by the internal parts. So all the ports have to be delegated, input and output ports have to be delegated. So in this way, I have completed my my hierarchical refinement of the component, of the WPS component in these parts. Of course, I could go on. So the next step will be to go on if needed with the composition of this unit. So yes, so what I have not represented here is the fact that when I had defined the BSU and hydraulic, I have just defined the ports. But what I have to do here, together with the port, is to provide the contacts for the block as the same steps that I have shown for the WBS system. So it is important. It is important. First of all, to define the block with its interfaces and so the ports, and also the contracts, and then you can go on with the decomposition. Indeed, let me just to show my final part of the presentation, which is related to the refinement of the contract. Let me show you the same model, but more complete. So here you can retrieve some information that I've created in a live mode, I would say. And so here you can retrieve the wheel-backing system, which is made by some more elementary parts. So you can retrieve here the ports, input output port, and also you can see that we have the contact associated to the wheel braking system top level, which is this one. But I also contracts associated to the associated to the other entity. So you can see here. So we have also contract associated to BS, to the control unit, and contract associated. A contract associated to the hydraulic. You can imagine that this contract formalizes some requirements that can be attached to the control unit, and requirements that can be attached to hydraulic. And these requirements is typically derived by some requirement analysis, starting from the requirements, top level requirements that, for instance, I showed you before for wheel braking system. So basically, at the requirement level, we will have some kind of the decomposition of the requirements. So for requirement, for more complex to lower level for fine-grained requirements. This kind of decomposition can also be reflected here at the level of the contracts. So, in particular, I can state how a contract of a decomposed system is actually covered by the contracts associated to the parts of the system, of the block itself. And to model the contract decomposition, I have to select the contract. Once I have the model, so all the decomposition and all the contracts for the top of the internal parts, I have to select the contract for the decomposed block. Right click and select contract, set contract refinement. And here the tools shows me the contracts that are available in the declared parts of the decomposed block. So here I have two contracts defined in the BSU part and one contract defined in the hydraulic part. Here I have to select the contract that I want to I think can be decompose this contract, and press OK. And I can retrieve this information by selecting the contract here. Go to by going into the profiling, the profile tab. Here I have this attribute associated to the contract associated to the block, which is the refined by attribute, which is filled by the action that I've shown you before. So here we have the information about how the contract of this decomposite part is actually refined by the contracts of the parts. Here I have selected all the contracts that are provided by the parts. I could have selected the subset, so because it is this is actually, as I was saying, it's not mandatory that, of course, that one contract has to be fulfilled by all the contracts, but it could be just a subset of the contracts provided by the parts. So, given also this is you can think about that the blocks here can cover more than one requirement. So in this case, you could have a list of contracts and the contracts that typically where the contracts can be associated to different requirements. So basically, the refinement of the contracts follows the refinement of the requirements that are formalized by the contract itself. And okay, this information in this is particularly useful because then this information can be used by the analysis, which are supported by chess, also in connection with the OCRA tool. In particular, this information can later be used to formally prove that the composition of the contracts is correct. This decomposition can be formally proved, and by having this guarantee about the decomposition, it is possible to prove the correctness of the system by just reasoning about the correctness of the contract associated to the parts. And the correctness of the contract of the top system is derived according to the correctness of the decomposition that has been proved by using the formal approach provided by OCRA. But this will be a feature that will be shown not in this training session, but will be shown in different training session dedicated to this the part of the analysis support. So I think that no, yes, they were next. I have finished my part. I think Alberto, the presentation on role can be moved to Alberto, that can say something more about tool support for contract-based refinement modeling.
Okay, so I move the presenting rights to Alberto.
Okay, can you hear me?
Yes, we can hear you.
Okay, so so basically at the stage of the workflow, we have performed different activities. So we started defining the formal requirements, then we defined the system component, then we decompose the system into one or more sub-components. Then we define the contracts and we perform the contract refinement. So at this stage it is important to have an overview of all those activities. And for this purpose, there are two views that are available. So one view in particular, it's about the architecture decomposition, the system decomposition, and that is called system hierarchical model view. And the other view is about the contract refinement, and it's named contract refinement view. So now I'm going to show you in chess how to open those views. So this is the WBS example again. And here on the bottom you can see the hierarchical model view, and here it's possible to see just in one picture how the system is decomposed into subsystems. So here you can see the system that is that represent the system component. It's possible to explore the system and see how is decomposed. So here, for example, we can see that the system is decomposed into two subcomponents. And then we can explore again each subcomponent to see how each component is decomposed. It is possible to see also which are the contracts that are associated to each component. So this is the purpose of this view. The contract refinement view is another view that enables to see how each contract of the model is refined. So here we have the contract associated to the system component that is called break time, and in this view it's possible to see how is refined. So in this case, this contract is refined by three other contracts. And again, it's possible to explore each contract to see how is refined. And here it's possible to see also that there are this icon that is basically it represents a weak contract. So in this view it's also possible to see which are the strong contracts and which are the weak contracts. So basically that's it for my side. The last thing is that if you don't have those two views open when you open the chess, you can find them in Windows Show View, Other. In the Papyrus folder, you can select one or the two views and open in the in chess. So, if you have question about this last part.
Questions? This part or any other part from Stefano? No questions? Last chance? Okay. So thank you, Alberto. Thank you, everybody, for joining in. And see you in the next session. This is this afternoon, 3 p.m. Work Package 4, Session 2, and Work Package 5. In the same slot. Okay? Thank you.
Thank you. Bye-bye.
Thank you. Bye.
Thank you, everybody. Bye-bye.